Good morning, guys. So in previous lecture we have derived the elemental stiffness or conductive stiffness matrix for the heat transfer problems. Okay, so in previous lecture we have derived this stiffness matrix. Okay, this is nothing but your stiffness matrix. It is called as stiffness matrix, or you can say elemental conductive stiffness matrix. Elemental conductive stiffness matrix, or you can say conductance stiffness matrix also. So this is your elemental stiffness matrix for the heat transfer problem. This is your temperature vector. Okay, so in structural problems we have seen that there is a displacement vector. Now instead of displacement vector there is a temperature vector, because we need to find out the temperature distribution within the element. Then next, this is your load vector due to heat generation. Okay, due to heat generation, because this Q is what? In watt per meter cube. This is the heat generation rate given in watt per meter cube. So load vector due to heat generation rate. This is your load vector. Then next, this is your boundary condition. Actually, this is your boundary conditions. That is heat flux going inside the surface or heat flux going outside the surface. Okay, so it is taken positive when it is going inside the surface, and it is taken negative when it is leaving to the surface. Okay, so depending on that, the signs will be there for this boundary condition vector. Okay, so based on this equation, okay, here A is actually A should be there. A is present here. So you can eliminate A also, but Kx into A divided by L, similar to your E into A divided by L, we are taking A here only. Nothing. There is no reason to take A, because to remember, similar to EA by L, we can write Kx into A by L. So we are taken A, area A is there. Okay. So Kx into A divided by L into 1 minus 1 minus 1 1. This is your elemental conductance stiffness matrix, and this is your load vector due to heat generation rate, and this is your load vector or intensity boundary condition due to the heat flux going in and going outside the surface. Okay. So based on this, now we will try to solve one example. Okay. So example is what? A circular rod shown in figure has outside diameter of 60 mm. Okay, here a circular rod is given. Circular rod is given of 60 mm diameter. Diameter is equal to 60 mm. Length of 1 meter. Length of this diameter is the length of this rod is 1 meter. And preferably insulated on its surface, means on circumference it is insulated. It is insulated on its circumference. The left half of the cylinder is of aluminium. Left half. Okay, this is 1 meter. So left half. So it is of 0.5 meter and 0.5 meter. Okay, so left half is of aluminium material. So this is of aluminium material which has Kx equal to 200. So which has Kx or K aluminium is equal to 200 watt per meter degree Celsius, and right half of material copper which has Kx is equal to 389. So K copper is equal to 389 watt per meter degree Celsius. The extreme right end of the cylinder is maintained at temperature of 80 degrees Celsius. So extreme right end, it is maintained at temperature of, so this end it is maintained at temperature of 80 degrees Celsius, while left end is subjected to heat input rate of 4000 watt per meter square. So left end it is maintained at input rate of 4000 watt per meter square. Okay, so using 4 equal length elements. So using 4 equal length elements, determine steady state temperature distribution in the cylinder. Determine the steady state temperature distribution. Steady state temperature distribution in the cylinder. Okay, so this is the data given for this example. So what is? It is a cylinder which is made up of half part is made up of aluminum and half part is made up of copper, for which the thermal conductivity K aluminum is given 200, K copper is given 389. Then they have said that the circumferential area means circular area is insulated. So this part is insulated, and also said that the heat input rate of 4000 watt per meter square it is given or maintained at left end, and the right hand temperature it is maintained at is equal to 80 degree Celsius. Also the diameter is given 60 mm. Then use the 4 equal length elements and find out the steady state temperature distribution. So 4 equal length elements is what? This is half part. So make two parts of this aluminium material and make these 2 parts for this copper material. So if we draw the free body diagram for this problem, then we will get 4 elements. Like if we draw a free body diagram, so this is first, second, third and fourth. First element, second element, third element and fourth element. Okay, so first, now this end is maintained at temperature T is equal to 8 degrees Celsius. So if we suppose take temperature T1 for this case, this is your T2, this is your T3, this is your T4 and this is your T5, and T5 it is maintained at 80 degree Celsius. Then so there are 5 nodes, 1, 2, 3, 4 and 5, because there are 4 elements. There should be 5 nodes in this. From this problem you will get the 5 nodes because there are 4 nodes, 4 elements. So also from boundary condition point of view, it is given that heat input rate Qx1, it is given that input rate it is entering into the surface, so it should be taken as positive 4000. Okay, and let us suppose if there is a heat input rate which is going outside from this surface, then we should take this as a negative. Okay. So here it is given as input rate, so we need to take it as a positive. So from this you will get, this is total 1 meter. Now we have converted this into 4 elements, so each element will become of 0.25. Okay, so each element will become of length equal to 0.25. So this is your free body diagram for this problem. Now we need to find out the temperature distribution. Okay, here diameter D is 60 mm, so it will become 0.06 meters. Also Kx for this 2 element, Kx is same, means K aluminum we need to apply. So K aluminum is equal to 200 watt per meter degree Celsius, and for this 2 element we need to take those same thermal conductivity, that is K copper, which is given equal to 389 watt per meter degree Celsius. Okay, so this is the basic data related to your problem. Now we need to find out the temperature distribution. So how to find out, or how to proceed to find out the temperature distribution within the field. Okay, so for this first we need to find out from this equation how to apply this equation to this problem. Okay, so here this is your elementary stiffness matrix. Okay, as there are 4 elements, we need to find out the elementary stiffness matrix for these 4 elements. Okay, this is your elemental conductive stiffness matrix. So we need to find out 4 elemental conductive stiffness matrices for these elements. Then we need to globally add this as previously done in your spring or bar system. Okay, so just similar to this procedure, we need to assemble these 4 elemental stiffness matrix globally. Then we will get global stiffness matrix. Then finally, your global stiffness matrix. What is the order of this global stiffness matrix? So as we know that how to find out the order of this global stiffness matrix. First we know that there are how many number of nodes are there? So as there are 5 nodes, as there are 4 elements, so number of nodes is equal to 4 plus 4 is equal to 5. So it should be of 5 by 5. It will become, or order of that matrix will become equal to 5 by 5 because the number of nodes in the system is equal to the order of that matrix depending on your degrees of freedom, because here only temperature T1 is the degree of freedom. Okay, so only 1 degree of freedom is acting on this one node, so this will become a 5 by 5 order. Okay, so this should be equal to 5 by 5. Then you will get into temperature distribution like T1, T2, T3, T4 and T5 is equal to, this is the boundary condition. Okay, so this boundary condition, it should be applied at every element. We need to apply this boundary condition at every element. Okay, actually this is a load vector, so we need to find out this load vector for each element. Okay, but here in this problem, the heat generation source or heat generation sink is not mentioned in this problem, so simply it will become equal to 0. But if the heat generation rate is present in the problem, then how to determine the heat generation rate? We will see this in next problem. Like I will just say that how to determine, or I will just explain how to determine this load vector similar to your load vector in your spring or bar system. So how to determine? So for each element, as there are 5 elements, so first we need to find out the load vector for this element. You will get first load vector, that is 2 values. Then we need to find out the load vector for this second element. Then for this third element. Then for this fourth element, and then this for this fifth element. And then we need to globally add these elements. It means what? This first 2 values plus these 2 values plus this means what? 1, 2, 3, 4, 5. So you need to write down first 2 values here, then second, then third, then fourth, and then fifth. Likewise, you will get this load vector due to heat generation. So, but in this problem, heat generation source is not mentioned. So this will become simply equal to 0. Okay. So we will see such type of problems in your next such type of procedures in your next lecture or next problem. So here just we will try to solve this temperature distribution due to heat flux inside the surface going inside the cylinder only. Okay. So in this way, this will become equal to 0 because heat generation source or heat generation sink is not given. Suppose if there is a heat source, then you need to take it as positive, because, and if there is a heat sink, then you need to take it as a negative. Okay, we will explain this term in next lecture. Now this Qx1 and Qx2. Now we need to concentrate on this boundary condition. Okay, so boundary condition, what are these boundary conditions? So at first node Qx1 is given, and at last node it is not mentioned. So we need to find out this heat going outside the cylinder. Okay, so this will become your boundary conditions. So boundary conditions will be applied at extreme left and extreme right. Okay, so at extreme left, Qx, it is going inside and its value is given equal to 4000. And at extreme right, it is not given. It means what? We need to find out this value. So this value of Qx out, we need to find. So boundary conditions will become Qx in is equal to 4000, and for remaining remaining equations it will become equal to 0, and finally qx out we need to find out. So this will become your boundary conditions. Okay. So by putting these boundary conditions into these equations and by applying the penalty approach, you will get the remaining equations, and by solving these equations you will get the answer. So okay. So we will proceed to find out the temperature distribution within the element. Okay. So how to proceed? Here, first we need to find out the elementary stiffness matrix for each element. So first, for first element, we need to find out elementary stiffness. Okay, for first element and second element, the properties are same. It means the length is equal to 0.25 for this element, also for this element it is equal to same. Similarly, the thermal conductivity value is also same. So K aluminium is equal to 200 and the length for these two elements is equal to same. So for first and second element, we will get K1 is equal to K2 is equal to K aluminium into area divided by L. Okay, into 1 minus 1 minus 1. So in this way you will get K aluminium is equal to 200 into pi by 4 d square is equal to 0.06 square divided by length is equal to 0.25 into 1 minus 1 minus 1. So for this first and second element you will get K1 is equal to K2 is equal to, so this if you calculate this value you will get I think 2.26. This value is equal to 2.26. So you will get K1 and K2 equal to 2.26 minus 2.26 minus 2.26 and 2.26. So this is your first and second elementary stiffness matrices. Now for third and fourth stiffness matrices, we have K copper is equal to 389. Both K copper it is applied for both elements. Also the length of this element is also same. That is equal to 2.25. So if we calculate this K3 and K4, K3 is equal to K4 is equal to. Now here only change is what? Instead of aluminium, it will become copper. So it is equal to 389 into pi by 4. Area is same, 0.06 square divided by length is 0.25 into this matrix. So this value equal to this value is equal to, I think we will get this value equal to 4.40. So 4.40 it is equal to 4.40 into this matrix. So 4.40. So you will get finally the elementary stiffness matrix for third and fourth element as, so K3 is equal to K4 is equal to 4.40 minus 4.40 minus 4.40 and 4.40. Okay, so as we know that now we need to assemble these elemental stiffness matrices now. So here how to assemble these elemental stiffness matrices. Actually we have studied how to assemble the global stiffness matrix by using the elemental stiffness matrix in your spring as well as bar element. So the global stiffness matrix, as there are 4 elements, so this will become equal to T1, T2, T3, T4 and T5 like that. Okay, so this is your first, second, third, fourth and fifth position. Similarly, this is your first, second, third. Okay, 1 second, because it is a 5 by 5 matrix. This is your first, second, third, fourth and fifth position, and this is your first, second, third, fourth and fifth position. So as we know that your first element its value is this matrix. So first element is in between node 1 and 2. So place this matrix between these positions, because this is position between the actual connectivity of this element is in between node 1 and 2. So we need to place the value here only. So 2 point, it will become 2.26 minus 2.26. Okay, so values are like that. So 1, 2, 3, 4 and 5. Similarly, 1, 2, 3, 4 and 5. Okay, so 2.26 minus 2.26 minus 2.26 and 2.26. Now, second connectivity of second element of stiffness matrix is in between node 2 and 3. So between node 2 and 3, between node 2 and 3. So this will be placed at this position. So plus 2.26 minus 2.26 minus 2.26 plus 2.26. Now for third element, the connectivity is in between node 3 and 4. Means between 3, we need to place it between 3 and 4. So this is the connectivity. This is the connectivity. So plus 4.40 minus 4.40 minus 4.40 and 4.40. And for last element, its connectivity is between 4 and 5. 4 and 5. So this is the connectivity. So plus 4.40 minus 4.40 minus 4.40 and 4.40. Okay, so it will become 4.52. This will become 6, 4, 2, 6, 6.66. 6 point, this will become 6.66. This value become 8.80. Okay, so in this way you will get this global stiffness matrix. Remaining terms are 0. Okay, so in this way you can write your elemental stiffness matrices is equal to, with the help of this temperature vector and load vector relationships, we can write this matrix into temperature vector is equal to this. As we know, this will become 0 because there is no internal heat generation source or sink in the cylinder, so it will become 0. And now finally this is the boundary condition is equal to area times, it is nothing but 5 by 4 into 0.06 bracket square into this value qx1, qx in 0, 0, 0 and qx, it should be negative because it is going outside the value. So here unknown value is equal to qx up. So which one is unknown? We need to eliminate this row and this column. So on RHS side, so if we multiply this area to this qx in, so pi by 4. So this value is actually what is this value? Pi by 4 into 0.06 square. This value is equal to 11.31. Okay, 1 second. This area is equal to, I think, what is the area? qx is equal to, we can put 4000 because its value is equal to 4000. It is 0, 0, 0 and qx out we need to find. Okay, so now this value is unknown. We need to eliminate fifth row and fifth column. So if we eliminate this fifth row and fifth column by applying the boundary condition, if we eliminate this fifth row and fifth column, only 4 equations will be remaining. 1, 2, 3 and 4. Okay, now here let us see. As we know that T5 value is given equal to 80 degrees Celsius. Okay, so if we write these 4 equations into the equation format, okay, so if we write these 4 equations in equation format, after elimination, fifth row and fifth column, we need to write down these 4 equations. Okay, so these 4 equations will become 2.26 into T1 minus 2.26 into T2, 0 into T3, 0 into T4, 0 into T5. Okay, so due to this 0, there is no effect. Similarly, for the second equation, up to this, we have T4. Now for this, due to this 0, there will not be any effect of this T5. For this third equation, this first 4 values up to T4 we can write. Also 0 into T5, so it will become 0. Now for fourth equations, if we write the fourth equation as 0 into T1, 0 into T2, minus 4.40 into T3, 8.80 into T4 and minus 4.40 into T5. It means what? If we eliminate this 11, so we need to take account this 11th value because T5 is equal to 80 degrees Celsius is given and it is equal to known value, and this effect we need to add in this fourth equation. It means what? Minus 4.40 into 80. So this will become, so for your fourth equation will become 0, 0, minus 4.40, 8.80. It means 0 T1, 0 T2, this T3, this T4, it is plus, minus, plus and minus this 4.40 into 80 value is equal to this 0. Actually this area into this is 0. So but here the effect of this we need to take into account because for first 3 equations there are 0 values for the fifth column, but for fourth equation there is a value, so we need to take account, we need to take this value into account. So this will become equation, finally this equation will become 0 T1 plus 0 T2 minus 4.40 T3 plus 8.80 T4 is equal to, now this value comes to the right hand side and it will become 4.40 into 8. Okay, so now if we write this equation into this matrix, then you will get this value as 0, and instead of this 0, now you will get, instead of this 0, you will get 4.40 into 80. So this is nothing but 352. Okay, so 4.40 into 80 is equal to 352 instead of this value. Okay, so actually first here it is 0, but plus it will become 352. So this 0 plus 352 finally will become 352 because in this equation plus this value for this fourth element also. Fourth. Okay, so this will become 4000 into this area, this will become 11.31. 11.31. So 0 into this area, 0 into this area, 0 into this area plus 352. This will become 350. And this QX sum, this will become equal to minus 0.0028. Minus 0.0028 QX out. Okay, so as we have eliminated our fifth row and fifth column, we will solve only this 4x4 matrix. Only this 4x4 matrix. After taking the effect of that element, this will become 0 and this effect will be transferred to the RHS side, so it will become 352. So finally, this will become So you can write here only. So simply you can write this as this is your T5, which is equal to 80 degrees Celsius, is equal to 11.3100352, and this is your minus 0.0028 Qx out. So this is eliminated. So this 4x4 matrix into T1, T2, T3, T4 is equal to 11.31000352. So by solving these four equations in a matrix or in your calci by using matrix calculation, you will get T1, T2, T3 and T4 values as T1 is equal to T2 is equal to. So you will get by solving these four equations by Gauss elimination method you can solve it, but by simply in your calci you can solve it by using your matrix calculation. So if you take a 4x4 matrix calculation, then you will get T1, T2, T3 values as T1 is equal to 95.50 degrees Celsius, T2 is equal to 90.40 degrees Celsius, T3 is equal to 85.15 degrees Celsius, 85.15 degrees Celsius, and T4 is equal to 82.57 degrees Celsias, and T5 as well as that it is 80 degrees Celsius. So how to cross check your answers? Here only you can just by looking the results you can confirm that your results are correct. Like that, as you know that heat generation rate is going from left side to the right side. So heat is decreasing from left to right hand side. So here temperature values are decreasing from left to right. Okay, so your answers are correct. And finally, you can find out the heat going out, Qx out, by using this last equation. So for this equation, first the values are 0, minus 4.40, minus 4.40 into T4 plus 4.40 into T5. Okay, minus 4.40 T4 plus 4.40 into T5 is equal to minus 0.0028 Qx out. So by using this, you will get this value, and this value is equal to Qx out is equal to 4038 degree, 4038 watt per meter square. Watt per meter square. So in this way, you can find out the Qx out also. So by using by using this elemental stiffness matrix and these boundary conditions, you can find out the T1, T2, T4 values, and finally by using this fifth equation you will get the Qx out. Okay, so heat conducted must be equal to heat going out. So here let us look at this 4038 watt per meter square. So heat going inside is equal to 4000. It is nearly equal to 4030. So your answer is okay. So in this way you can find out the temperature distribution within the element for your heat transfer problem. Okay. So I am just concluding this lecture here only now, and we will see some another time in your next problem. Okay. So thank you.